Okay, everyone, this is Scott Reeves. This is FSN 329, and this is our lecture on calcium. I'm going to go for probably about 45 minutes on this. That way we'll catch up on the part that we missed tonight. And so here we go. Here is the calcium lecture outline. We're going to talk about dietary sources and intake of calcium. We're going to talk about absorption, supplements, role in bone health, additional roles of calcium. We'll go through just a couple of examples of that. Then hormonal regulation, calcium excretion, and then calcium deficiency, toxicity, and status. And as we go through this, I kind of want to apologize. I'm in my office at home and I'm actually multitasking on some stuff. So I might have to stop every once in a while and kind of restart. So bear with me on that. So let's look at the first one now. This is a chart that shows the minerals, and we looked at this before, and it has kind of an upper part to it and a lower part. See if I can get my cursor there. The upper part of this panel now has some of the major minerals, and the lower part we talked about before that has iron. And one of the things we talked about the major minerals are that the reason they're called major is not only because they are required in higher amounts in the diet compared to the minor minerals or the trace minerals, but also because they are more abundant in the body. And so, for example, one way of defining the major minerals are those that are present in amounts larger than 5 grams, which is about a teaspoon, in the body. And a pound is about 454 grams. So only calcium and phosphorus appear in amounts larger than a pound. So a few things to take from this chart. One is there are various definitions for the major minerals, and one of them is this, that they are present in amounts larger than 5 grams in the body. Another one is that they are required in the diet in greater than 100 milligrams a day. And the most abundant mineral is calcium by far. It's almost twice as much as phosphorus. And then phosphorus levels are about approximately half of calcium, but I want you to remember that phosphorus is the second most abundant mineral in the body. And both those minerals are in such high amounts because of their role in bone. And we'll talk about their specific role of bone coming up. But remember, these two go together. It takes both adequate amounts of calcium and phosphorus to make bone and to maintain bone. And in the diet, most people typically get adequate amounts of phosphorus. But calcium tends to be something that is a real challenge to get for a lot of people. So that can be what actually compromises bone health and bone integrity in a lot of individuals. So we'll talk about that. All right. Now let's talk about calcium food sources relatively quickly. So we'll kind of get right into this. Now I adjusted this diagram. The DRI for calcium is an RDA. And so I want you to remember that. And this changed. The DRI for calcium intake changed in November 2010. It went from an adequate intake to an RDA. And these are the current values. So for example, the RDA for women ages 19 to 50 is 1,000 milligrams of calcium a day. For men, the RDA is for men 19 to 70 years of age is the same, 1,000 milligrams a day. But if you look at this above age 51, so between 51 and 70 or greater than 51 for women, it goes up to 1,200. So the point is, in 19 to 50-year-olds, it's the same for men and women. But then for when women turn 50, they require more calcium than men. It goes up to 1,200 for them. For men, it stays at 1,000 until they're greater than 70 years of age. Now, is it easy to get that much calcium in the diet? It actually is. Depends on the diet. So what we're going to remember for calcium sources is that the best sources of calcium in the diet, we're going to remember dairy products, shown here. So we're going to remember dairy products, including milk, yogurt, and cheese. Okay, so milk in general has approximately 300 milligrams of calcium per cup, which is a relatively high amount. For yogurt, 1 cup of yogurt has approximately 450, so that tends to be a good source of calcium. Now, that's kind of a typical yogurt. The Greek yogurt actually has a slightly lower amount of calcium than normal yogurt. It's part of the purification process for the Greek yogurt. It has higher protein, it actually has a little bit lower calcium than normal yogurt. And cheese, let's see, they have, boy, this is a little bit off, but 1.5 ounces of cheese, which is about a square cube at about 1.5 by 1.5 inches. That has about 300 milligrams, so that would be comparable to a glass of milk. So if a person is not consuming dairy, then that can be a real challenge to get calcium. In general, of course, we want people to get adequate amounts of calcium from their diet rather than supplementation, but for a lot of people it's appropriate for them to supplement with calcium. So we'll talk about that as well. Okay. Now there is a UL for calcium, and the UL we're going to say for adult men and women ages 19 to 50, the UL is 2,500 milligrams. Okay, so the UL for adult men and women ages 19 to 50 is 2,500 milligrams. Okay, so generally that's not a problem for dietary intake, but sometimes it can be a problem with supplements. So that's something for them to keep in mind. Okay, let's see. And you can see overall, some of these food products are relatively low. So fruits and vegetables, that's one of their weaknesses, is they're actually relatively poor sources of calcium. Exceptions are shown down here, and the reason that these sardines are high is because it's actually with bone. So if a person's consuming that, or sometimes a soup that's actually made with fish with the bones in it, is high levels of calcium, but that's not all that common. So best sources, dairy. Another potential source is fortified foods. Fortified foods that are specifically fortified with calcium, and that's the example here would be, for example, tortilla has relatively high amounts, but I think we've seen this, like fortified orange juice with calcium and some other fortified fruit juices. They can actually become an important source, especially if someone is avoiding dairy products. Okay, so let's look at the next one. So this shows kind of what I mentioned before. This is calcium in milligrams per day, and unfortunately the wrong DRI is on here. This is an older slide, but I kept it because I think it has a good way of looking at this. So if we go over here, and this is what we need as far as calcium milligrams per day. Here's our adult range that we just talked about. Here's our age down here, so approximately 19 to 50-year-olds. Here's our 1,000 milligrams per day. And this is what we actually get. And again, this is in the US. So it's not uncommon for people to be consuming approximately half of their recommended daily or dietary allowance, because this is actually AI, but this is the RDA for it. So relatively common for people to be consuming approximately half of their calcium requirements per day. And again, this would just be from food. Okay, so it is a relatively common problem. Okay, so one of the things we're going to talk about is how calcium is absorbed. And in order to do that, we're going to look at 3 main absorptive processes, and those are shown here. And I'm going to give you some details on each of these. And so as we go through this, it's kind of listed out here, and then I think what I'll do is I'll probably skip to the next slide, which has this in kind of a diagram. So 3 main absorptive processes for calcium, right? So let's say, for example, we consume the calcium, it goes through the stomach and then into the small intestine. So most calcium absorption is in the small intestine, probably more in the jejunum than the other parts of the small intestine. And one of the main systems is the calbindin system. We've talked about that a lot. That's regulated by vitamin D. It requires energy, and it is saturable. There's another system called the paracellular system. So basically this means between cells, calcium can actually diffuse. It is non-saturable because it's diffusion based, and the mechanism is not well understood, and it's not sure exactly how much calcium absorption takes place, but it can be significant. The third one listed here is the most significant of the three, and that's the endosomal lysosomal pathway. And I'd say even less is known about this by far than the other two types of or mechanisms of absorption. And it appears that calcium enters a cell by endocytosis, and then it's transported through the cell by lysosomes, and then it exits by exocytosis. Okay? And there's also some absorption in the large intestine. There's bacterial fermentation of fibers that are bound to calcium. So sometimes fiber binds minerals in the gut, and some of those minerals that would include calcium. So calcium can go through the small intestine unabsorbed, go into the large intestine. When the bacteria ferments the fiber, it releases the calcium. Now this is, I think, kind of a maybe an exaggerated percentage, but this says 4 to 10% of dietary calcium is absorbed that way. I think it's probably less than that, but that means that of the calcium that's absorbed, that's where it actually is absorbed through in the large intestine. So it accounts for some of the calcium absorption. Let's look at these more specifically. The first one that we're going to look at, here's the calbindin system. So if we orient what this slide is showing, we have the lumen of the small intestine, brush border membrane shown here, enterocyte, single enterocyte here, basolateral membrane, portal vein. So after the calcium goes in here, it would basically be in the blood, transported to the liver. Here's the calbindin system, and this doesn't show it. Your textbook actually has a modified diagram of this that shows a calcium channel. So let's go through this one. At the brush border membrane, calcium can be transported through a calcium channel. So there's a protein here. Calcium goes through the channel into the enterocyte. In the cytosol of the enterocyte, calcium binds to the calbindin protein. And they've drawn it to look like a little boat here, actually a ferry. Isn't this cute? Because the calcium is actually ferrying the calcium. The calbindin is ferrying the calcium through the enterocyte to a calcium pump on the basolateral membrane. So calbindin hands the calcium to the calcium pump, which uses ATP to move the calcium into the portal vein. And one of the reasons this is important is, number one, this active transport out of the cell is important because a lot of times there is a gradient where there's a lot more calcium, free calcium in the blood than there is in the cell. As a matter of fact, sometimes it's somewhere between 1,000 to 10,000 fold higher calcium concentration in the portal vein than there is in that enterocyte. So it is going against a significant concentration gradient, and the pump allows that to happen. Another reason this is important is because this calcium pump is regulated by vitamin D. Right? So the calcitriol increases levels of the calcium pump protein. And of course, calcitriol also increases the levels of calbindin protein. So vitamin D can increase calbindin and the calcium pump so that it facilitates calcium absorption into the portal vein. Now, under moderate levels of calcium intake, calbindin system is probably the most important transport system. When I say moderate, I mean a few hundred milligrams, for example, of calcium. So normal dietary intake would be this system. Now, this system is saturable. So let's say a person takes a calcium supplement, let's say it's 1,000 milligrams of calcium. This transport mechanism can become saturated. Okay? The saturation appears to occur at approximately somewhere around 100 to 120 milligrams of calcium in the gut at the same time. If there's more than that, this system starts becoming saturated. When this system is saturated, another system that becomes more significant is this one over here, the paracellular pathway. So when calcium levels are really high in the gut, more than 120 milligrams especially, the paracellular pathway becomes more significant, and that's where the calcium basically can diffuse in between the enterocytes to get to the portal vein. So if a person takes a high amount of calcium in a supplement, that tends to be a really important pathway here. Now, it's not sure how exactly that works, but it can make a significant contribution when high doses of calcium are consumed. Okay? Another system is shown here. Here's the endosomal lysosomal pathway. And it appears that, and this is really not very well understood, calcium can bind to the brush border membrane. It's actually endocytosed, forms a vesicle or an endosome, starts moving through the cell, kind of fuses with the lysosome, and then this endosome lysosome component moves through the cell to the basolateral membrane where it exocytoses calcium into the portal vein. Okay, so it appears this is also a mechanism, but it seems overall this is the least significant of the transport mechanisms. Okay, but one thing to keep in mind is in cells, calcium is typically always bound to a protein or it's part of an endosome, because calcium in a cell, if it's free, can bind proteins and alter the structure of proteins. And one of the reasons that's important is because calcium is used as a secondary messenger inside cells. So cells really control the amount of free calcium that they contain, and they minimize that by using certain mechanisms. And that's so that calcium doesn't activate signaling pathways in an unregulated way. Okay? So I think that's enough detail on that one. Overall, efficiency of absorption of calcium is approximately 30% in adults. Okay? And that can vary significantly though. During certain times of development, then this percentage of calcium absorption efficiency can go up to something like 60 or 70%. But overall, on average, about 30% of calcium that's consumed is actually absorbed and is bioavailable. That's the basis of the recommendation. So when they say consume 1,000 milligrams, that means that is the amount that needs to enter your gut. And from that, they're assuming approximately 30 milligrams of calcium is actually going to make it into the tissues and is bioavailable. Okay? The percentage absorbed depends on the actual source of calcium and some other factors. So one of the things to think about is, what are the differences between calcium absorption of supplements versus foods? Calcium supplements are one of the most common supplements on the market, as you can imagine, and they're usually sold as compounds with varying levels of calcium and bioavailability. In some studies where they test approximately 250 milligram dose, this is what they came up with. Calcium carbonate, which is a relatively common, inexpensive form of calcium, right, is about 39% absorbed. Calcium citrate, which is another very, very common source, is about absorbed in efficiency of about 30%. Okay, so there's some difference there. But overall, I would say calcium citrate is relatively well absorbed, approximately about the same as calcium from most foods. So that tends to be a really good supplement, and it's relatively pure. This is just calcium with citric acid attached. Negatively charged citrate binds to calcium, goes into the gut. It's basically, one way you could look at that, it's a clean, pure source of calcium. So I would say that is a good source of type of calcium supplement. We also have calcium gluconate, which is approximately 27%. So overall, when absorption, or when a dose is approximately 250 milligrams of calcium, then it can be absorbed at approximately the same efficiency as that from regular food. One of the things to think about is Some formulations may contain lead and some have poor bioavailability. For example, a person should not take oyster shell and bone meal preparations as a source of calcium. There's high amounts of calcium in here, but there can also be heavy metals, especially lead in some of these, but there can also be aluminum. So the better sources would be up here: calcium carbonate and potentially calcium citrate. A lot of times you'll see the calcium now with other things like vitamin D and magnesium, and sometimes zinc, some other minerals that are in there as well. So those can all be considered and maybe good options for some people depending on what they need as far as relative to their diet, right? What are some food factors that influence absorption of calcium? This is interactions between calcium and selected nutrients or substances. We have some things that nutrients or substances that enhance calcium absorption. And of course, the one we've talked about before is vitamin D, can significantly improve calcium absorption efficiency. Also sugars, especially those sugars in dairy products, can actually help improve calcium absorption. And protein can actually do that as well. I think the sugars and the protein kind of help keep the calcium soluble in the gut and help its absorption efficiency. Over here, some substances or nutrients that inhibit calcium absorption. We mentioned fiber. Overall, though, as long as a person's not consuming, mega doses of fiber, it's typically not considered to be a reason to decrease fiber intake to improve calcium absorption. Phytate and oxalate, these are negatively charged organic molecules that are high in some plants, especially vegetables, specifically something like spinach tends to have high amounts of oxalic acid, and they are negatively charged. They combine the calcium and decrease its absorption efficiency. So you're not going to find those really in dairy products. So depending on the source, that can or won't be problematic. Excessive divalent cations like zinc and magnesium, they can impair some of the absorption, and unabsorbed fatty acids. Now, of these, I would say potentially the problematic ones would be the phytate oxalate. And then over here, so this decreases absorption. Now let's look at some nutrients that enhance urinary calcium excretion. Things like sodium, for example, can be a problem. For example, it's not uncommon for some people to consume over 2 grams of sodium. And it's been shown that about 2.3 grams of sodium increases calcium urinary excretion by 40 milligrams. Remember, the RDA is 1,000 milligrams, so 40 milligrams is approximately, 4%? So I'd say that could be a problem, especially if some people consume more sodium than that. Protein can also increase calcium losses in the urine, and for example, one study showed that doubling the intake of protein, and this is pure protein, caused about a 50% increase in urinary calcium losses. Okay? But protein is a very important component of bone. So in general, as long as we're taking in, appropriate amounts of protein, we typically don't worry about that protein potentially increasing calcium excretion. Now, when protein is taken as part of foods, some other nutrients such as phosphorus tend to minimize losses of calcium. So it's, again, overall dietary protein is, I'd say, more beneficial than harmful as far as calcium metabolism. Okay, and we'll talk a little bit more about that coming up. The main route of calcium loss from the body is actually in the urine, and urinary losses range from approximately 100 to 240 milligrams a day, but urinary calcium losses tend to average about 170 milligrams a day in the urine, and so you can take the values I just gave you, for example, the 40 milligrams loss with high amounts of sodium, and put that in that context. So you can see how that could be considered significant. That may be increased slightly by the things we just talked about, including caffeine. For example, it's estimated that 1 cup of caffeinated coffee promotes loss of about 6 milligrams of calcium in the urine. Okay, so if a person consumes a lot of caffeine, that could contribute to their calcium losses. So it's important that they get adequate amounts of calcium in their diet. Fecal losses of calcium from endogenous sources basically is about 45 to 100 milligrams a day. And sometimes these molecules, for example, phytates and oxalates and fibers, they will actually bind the calcium, and that will increase losses of calcium in the fecal material. Okay? All right, so we'll talk about that a little bit more towards the end of this. So let's move on. Now, calcium transport. Once calcium goes into the portal vein, it's going to tend to be transported in the blood by a few different ways. The most common, or one of the most common ways that calcium is transported in the blood is actually binds to albumin. And prealbumin is kind of a precursor of albumin. Considered the same in this context, really. Now, this is a negative acute phase protein, and it can distort calcium assessment. So, for example, an acute phase protein is something like albumin. So if an individual is physiologically, or let's say immunologically stressed, protein synthesis of some proteins actually go up in that case, and we call those acute phase proteins. Albumin's one of those. So let's say, for example, albumin levels go up because of stress. That can actually distort calcium assessment. We'll talk about calcium assessment in a minute. Okay, so one of the ways calcium is transported in the blood, bound to albumin. About half of the calcium in the blood is actually ionized. That means free. It's charged. It has that +2 charge. And sometimes this is actually measured in the blood. It's considered to be a better measure of true calcium status than albumin or bound calcium in the blood. Some calcium in the blood, because it's positively charged, will actually complex with things like sulfate, phosphate, and citrate, negatively charged molecules in the blood. That's only about 10%. Okay, so overall, there's not really a specific calcium transporter in the blood. Some of it kind of binds other proteins, especially albumin, but not a real specific transporter. So what are some of the functions of calcium in the body? Most famous is probably calcium as part of the bone matrix, part of bone. It's also extremely important for nerve function. We'll talk about that a little bit coming up. So it's important in signal transduction. We talked about its role in blood clotting, so that's another important part. We're going to go back through and look at the steps in muscle contraction. We'll see the role of calcium there, so it's important for that. Cellular metabolism, there are a lot of proteins, including enzymes, that actually rely on binding calcium to perform a specific function. Some of these functions are so important to the body that our body will actually take calcium from the bone in order to maintain some of these other vital functions. So that's what we're going to talk about in a few minutes. Let's see. Overall calcium in the body. About 1% of calcium is actually in the blood and cells. And 99% of it is actually in bone and teeth. And the skeletal bones, some details about those are shown here. About 60 to 65% of bone weight is from minerals, calcium, phosphorus, and others. So when you look at your DEXA data, as a matter of fact, you guys still have that. When you look at that and it says your bone mineral content, let's say, for example, it was 5 pounds, that's not how much your bones weigh, that's how much the actual minerals weigh. That's only about 60% of bone weight, and most of it is calcium. Right, we'll look at that in a second. About 34 to 40% of bone weight is actually from water and organic molecules. For example, protein. The most common protein in bone is collagen. Two other very common proteins in bone is osteocalcin and what's called matrix GLA protein. And both of these are actually GLA proteins, right? They depend on vitamin K for carboxylating glutamate residues to form GLA residues, and that's how they bind calcium. So they're important for mineralizing bone. They'll bind calcium, they're actually proteins, so that forms part of the bone matrix. The bone, the skeletal structure, actually lends strength and rigidity to the body frame, and it also serves as a calcium bank, so it has those two roles. And another important thing to remember here is calcium is in the form of what's called hydroxyapatite. So you want to remember this formula. Hydroxyapatite are mineral crystals of calcium and phosphorus. Phosphorus is in the form of phosphate. Approximately 10 atoms of calcium per 6 molecules of phosphorus. So there's more calcium than phosphorus, about 10 to 6, and there are some hydroxy groups that are part of this. All right? Hydroxyapatite is one of the ways minerals are attached to protein to form bone. So these hydroxyapatite crystals actually attach to a protein collagen matrix, and that's what forms bone. So again, it's a relatively dynamic structure that we can make and degrade kind of on a 24-hour, 7-day-a-week basis. So it's consistently being made and broken down, bone is. So we're going to talk a little bit more about the structure of bone. And as I just mentioned, it's a dynamic material. It's constantly undergoing turnover, which is comprised of growth, basically bone mineralization, breakdown of bone, which is referred to as resorption, and then kind of the regrowth. It's consistently doing that depending on what's happening to the body as far as physical stress, dietary stress, hormonal stress. All of those things can impact what the end result is of turnover, whether or not we're adding bone or we're actually resorbing bone. And again, bone mineral density probably maximizes somewhere in the 20s. It's estimated anywhere from early 20s to late 20s is when bone tends to reach its maximal density, and after that, resorption tends to be more significant than growth. There are two main types of bone. There's cortical bone, which is typically the dense outer shell of bone, and of all the bone in our body, cortical bone is about 75% of the structure of all the bones in our body. Approximately 25% of the structure of bone is trabecular, and that's the spongy inner network of bone. And both of these structures, though, have specific roles. Trabecular bone is really important because it's lightweight, and it is still typically structurally sound, but because of its kind of honeycomb structure, do I have another picture of this? Maybe not. Down at the bottom here, if we look at this, it actually has a structure that's light, and yet it's resistant to breakdown, or it's resistant to shear forces. So you can put stress on this bone almost any angle, and because of this kind of honeycomb structure, typically it can resist those shear forces and maintain its integrity. Cortical bone is on the outside of bone, especially on the long parts of bone. Now, if it's a small bone, sometimes that particular bone, for example, some of the bones in the joints of your fingers and smaller bones in the body are typically all cortical bone. The longer bones, like in the vertebrae, long bones of the legs, and bones of the forearm tend to have higher amounts of trabecular bone. Trabecular bone is actually more metabolically active in general. So trabecular bone can sometimes be the most sensitive indicator of bone loss. But during bone loss, we do lose both. But it tends to be, in general, trabecular bone tends to be a little bit more likely to be lost during the process of bone loss. Let's see here. I have a little bit more on that coming up. There are three main types of bone cells. There are osteoblasts. They are bone building cells. Osteocytes, which are osteoblasts that have been incorporated into the bone matrix. There are osteoclasts, which are involved in bone resorption. So the osteoclasts basically break down bone. Osteoblasts and osteocytes help make bone and then maintain that bone. So we're going to talk about the regulation. All three of these bone cell types are involved in both cortical and trabecular bone metabolism. So let's look at osteoblasts and bone formation. This little diagram is pretty cool. This is actually in a dish where they're actually growing an osteoblast. You can see it's kind of reaching out here. Because one of the things to think about is, how do we study how these osteoblasts works? And that, I think you can imagine, is a really important part of drug development, is actually seeing how that drug specifically stimulates these osteoblasts. Now, in this case, what these osteoblasts do is they're actually synthesizing proteins and secreting those proteins, and they actually help those proteins become mineralized. So they're secreting substances onto those proteins that help hydroxyapatite and other minerals bind to those so that the actual bone could be formed. So they make the matrix proteins like collagen and osteocalcin. They're involved in mineralization of those proteins. These osteoblasts also have receptors on their cell surface, and they have receptors inside the cells. For example, they have vitamin D3 receptors. So osteoblasts respond to calcitriol. And when calcitriol binds to the receptors in osteoblasts, it promotes osteocalcin production, for example. And that's one of the ways that vitamin D helps bone formation. They also have estrogen receptors. And the binding to the estrogen receptors actually stimulates the osteoblast to synthesize bone proteins or bone-forming proteins. These guys also have receptors for parathyroid hormone. When parathyroid hormone binds to the receptors, it stimulates the osteoblast to signal osteoclast precursor cells. So in that case, if you think about it, when calcium levels in the blood go down, PTH is released. So when blood calcium drops, PTH in the blood goes up. That binds the receptors on osteoblasts. The osteoblasts kind of transmit the signal to osteoclast precursor cells so that more cells become osteoclasts. Osteoclasts break down the bone. Net effect, blood calcium goes up, and that's one of the ways that we restore blood calcium levels in the blood to normal levels so that it can go to tissues and perform required functions. Osteoclasts are shown here, kind of a neat little diagram of what they do. Osteoclasts are relatively large multinucleated cells. They'll have a number of nuclei, and they actually kind of sit directly on the cells, and they can degrade bone tissue by enzymes and acid secretion. So they'll actually make, for example, collagenase. They'll make enzymes to break down the bone proteins so that the minerals are released into the blood from the bone. They'll secrete acids to kind of help denature those proteins as well. For example, they'll make lactate, and I think they'll make citric acid as well to degrade that bone. And you can see they've actually created pits here. Once they're activated, they'll actually kind of bore down into that bone. They actually use their lysosomes to do this as well. So they're multinucleated, contain significant amounts of lysosomes, and they'll break down the bone when they're activated. They have receptors for calcitonin. Okay, so you want to be careful here. Calcitonin, I don't remember if I have this anywhere. I do. Calcitonin is synthesized in the thyroid gland. I think it's about 35 amino acids long or something like that. So it's basically a hormone. It's a peptide hormone. When it's released into the blood, it stimulates bone building activity of osteoblasts. So calcitonin stimulates osteoblasts, It inhibits the activity of osteoclasts, and it tends to inhibit the synthesis of calcitriol. This tends to happen when blood calcium goes up. Okay, so be careful. This is not calcitriol, this is calcitonin. So when blood calcium goes up, calcitonin is synthesized in the thyroid gland and it's released into the blood. That stimulates bone building activity of osteoblasts, and that makes sense because blood calcium is high. It inhibits osteoclasts because blood calcium is high, their activity is not needed. It also inhibits the synthesis of calcitriol, right? So it decreases activation of vitamin D, and that makes sense because blood calcium is already high. We don't need more vitamin D to increase calcium levels in the blood. Okay, so that's what that means. Okay, again, there is always a balance between osteoblast activity and osteoclast activity. In general, when we're younger, osteoblast activity is more significant. As we get older, osteoclast activity tends to be more significant than osteoblast. And of course, there are a lot of factors that affect that, but in general, that's kind of the balance that goes on through our life. Let's talk a little bit about bone turnover. We'll talk about loss of bone density. Bone turnover, as I just mentioned, kind of 24/7 combination of bone loss and bone gain, growth versus loss, cells involved. We went through those. Here's a classic picture. You guys have probably seen this before. Trabecular bone. This is in its kind of optimal, or what we would say characteristic structure. Over here to the right is trabecular bone that's lost significant mineralization. It can get to the point where this bone cannot handle up the normal forces that it needs to, and the bone can actually break. And sometimes this bone will actually break on impact when a person falls. Sometimes the trabecular bone will actually give way and cause the person to fall. But overall, we have a couple terms here. Osteopenia is a condition where too little bone mass at any stage in the life cycle. You actually measure osteopenia. One of the most common ways is you use the DEXA. And I believe the values are if a person has a T-score of between -1 and -2.5, they're considered of osteopenia. Depending on when it is in their life, it can be problematic. Osteopenia, a lot of times, if things don't change for that individual, can lead to osteoporosis. And osteoporosis is typically characterized or indicated by DEXA assessment. And when you do that, you typically use vertebral scan, lower vertebrae, because they have trabecular bone. So we do a different scan than we did in the lab. And sometimes you'll do the femur scan. You'll do basically the hip joint, because the upper femur has significant amounts of trabecular bone, and the DEXA will actually quantify that. And the software actually is different than we looked at. You actually use the software to quantify specific parts of the trabecular bone within that hip, the vertebrae, and also the forearm, and it will then give you a T-score. And a T-score of less than -2.5, for example, -2.5 or -2.6 or more than that is characterized as osteoporosis. Again, a lot of times it can be improved depending on what's going on with the individual, but sometimes that's actually hard to change. Okay, so osteoporosis literally means porous bone. Okay, so what about the prevalence of osteoporosis? Well, it is a major public health threat for about 55% of the 50-plus-year-olds, and that's about 44 million Americans. These numbers are a few years old. About 10 million individuals estimated to already have the disease. About 8 million of those are women. About 2 million are men. And so there's your 10 million. So do men get osteoporosis? Absolutely. It's less common in men than women, but they do get it. About 34 million more are estimated to have low bone mass, placing them at an increased risk of osteoporosis. Now remember, if we put this in the context of the U.S., there's about 310 million people in the U.S. About 44 million Americans have osteoporosis, or they're on their way to having osteoporosis. So it's a significant problem even in the U.S. It's responsible for, and I say that because, you know, in developing countries, it's even more prevalent, especially in certain developing countries with ethnic populations, such as, for example, Asian populations tend to have higher prevalence of osteoporosis. They tend to be smaller in stature, and that tends to lend itself towards less bone density. So one of the things that being larger in size, even obese, does is in some ways it can kind of help protect from osteoporosis because of that consistent stress or force on the bones tends to stimulate their metabolism. So that can actually help. Now, osteoporosis and low bone mass is responsible for about 1.5 million fractures annually. Of those, most common are the hip, vertebral, and wrist fractures. Of those, the most common fractures in osteoporosis is not hip fractures, it's actually vertebral. And that's actually twice as common as hip fractures. There are also wrist fractures where the individual a lot of times will fall and actually break their wrist. That's more commonly what happens here. Some of these vertebral fractures actually go undiagnosed, and the individual will have back pain and they're not sure why. They don't get scanned, they don't get it checked out. Sometimes they'll actually have a vertebral fracture that they're not aware of that's actually causing that pain. So that number might actually be a little bit higher than that. And again, this is just kind of an estimate, but it's a significant issue in the healthcare industry. So low bone mass and bone loss over time. Let me just finish these up real quick. Low bone mass and bone loss. So the name of the game in this case is maximizing bone density before losses start becoming more significant. So if we look at this, woman A entered adulthood with enough calcium in her bones to last a lifetime. Woman B had less bone mass starting out and so suffered ill effects from bone loss later on. So if we look at woman A at approximately age 30, her bone mass is up here. So as she goes from 30 to approximately 50 or 60 years age, basically about menopause, she's losing bone at a relatively consistent rate. Post-menopause, when they lose estrogen, women will tend to have an increased rate of bone loss for a few years. At approximately 60 years of age, it tends to kind of stabilize and go back to the same rate of loss as it was earlier in life. Okay, so this person ends up down here. She has enough bone density so that she's not osteoporotic. Woman B starts off with a lower bone density at age 30. Bone loss is the same here. Slope is about the same in each of these stages in life, but what that means, because she started lower out here in her when she's older, she's actually at the point where bone loss puts her in the osteoporosis category. So what are some of the risk factors for osteoporosis? The most common one, or the most important risk factor, is age. Okay, it's not gender, it's age. And that's just the strongest association. As we get older, our risk for osteoporosis goes up significantly. Low calcium intake can be an issue. I'll go through these in a second. Gender is an issue. Females, for example, have a higher risk than males because males tend to have denser bones, so there's more reserves upon which to draw as they lose bone. And women tend to live longer, probably 2 or 3 or maybe 4 years longer than men, and so that can result in higher incidence of osteoporosis. And again, we have menopause, which can decrease estrogen level, and then bone loss can actually increase more. So that slope of bone loss for men is actually, kind of more gradual for men than it is women. And part of that has to do with that protective effects of different hormones and the genders. Inactivity is an issue as well. That's a risk factor. For example, weight-bearing exercise stimulates bone formation. That says weight-bearing, but kind of any type of resistance training does as well. So weights, even yoga, things like that can actually improve bone retention, and that's really important. So I have running, walking, and sporting activities there, but it can be other things. So how do we prevent or decrease the risk of osteoporosis? Well, I'm going to give you 4 ways. One is actually a balanced diet, especially rich in calcium and vitamin D. So one of the first measures for prevention is consuming a balanced diet rich in calcium and vitamin D. A second way to increase or improve prevention of osteoporosis is consistently performing weight-bearing exercise. A third way to decrease risk of osteoporosis: do not smoke or drink excessive alcohol. Those are both risk factors, so we want to avoid smoking or excessive alcohol intake. And the third one is consistent bone density testing. That's one of the ways to do it, is kind of monitor bone density status. Okay, so I know you guys have talked about osteoporosis in a lot of classes, but so there's a little bit more information about it. The next slide is about regulation of calcium. I think that's probably all that I'm going to go through right now. So I'm going to conclude the lecture here, and then we will pick up on this in the next class. We'll finish up calcium metabolism. Okay, so I'm going to go ahead and stop this. So I hope this all went well.